Hi everyone, welcome back to Adrian's Digital Basement. On today's video we're going to get back to the Commodore 16, or affectionately known as the C16. I've had a previous video on this machine, so check the description, I'll put a link to that video. So let's take a look at what I have in store for today's video. Alright, here's my C16 hooked up to this HDMI monitor. I'm using a RetroTink 2X to do the video transcoding. So if I turn the computer on, comes on as normal. Commodore 16 has a reset button on the side, and if I push this and let go, just resets the machine. As you saw, it cleared the screen. But if I push it and hold it, the power LED blinks twice and I let go. And what the computer's doing now, it has switched into PAL mode. Now it's easy to tell it's in PAL mode. The top and bottom borders are a lot bigger. So it's currently running in 50 Hertz output. Luckily the RetroTink converts that and displays on HDMI without issue, but there is the machine running in PAL mode. If I turn the computer off, turn it back on again, we get double blink on the power LED and we're back in PAL mode. If I push and reset, hold the reset button down, we get one power blink on the power LED, one blink, and there we are, back in NTSC mode again. Basically, I'm able to switch between PAL and NTSC on this machine by holding down the reset button. So similar to the Commodore 64, the C16 uses a crystal oscillator to generate the video signal and determines whether you're going to be able to run in PAL or NTSC. So let's take a look at how I perform this trickery by simply pressing the reset button to switch between two different clock frequencies. Here's the C16 with the lid removed. I have shown here all the parts I need to do to mod it. Let's take a closer look. Here on the left is the SI5351 clock generator. It's a little inexpensive programmable device that allows you to generate any frequency like to use for a clock using a microcontroller. It has a pretty wide range of what it can generate, and I'll get to that in a second, but essentially this allows us to generate the clock frequencies we need. Similar to my Commodore 64 kernel switcher, I'm using a little clone Arduino board, sort of like the brains of the operation. I'll get to that code in a second. Here on the right, we have a 27C256 EEPROM, and it's installed in one of those sockets that allows us to have both the NTSC and PAL kernels installed at the same time. There are wires coming off of here, with the orange wire being the address 14 line that allows us to select between each of the two ROMs, of course using the Arduino, and the other two wires are plus 5 volts and ground, which allow me to power these devices directly off the socket. On the right you see a gray wire I have soldered onto this resistor. This allows me to pick up the reset signal that comes from me pushing the reset button on the side of the machine, and also allows the microcontroller to drive this line low to reset the entire computer. Unlike the Commodore 64, the C16 does not have a restore key, so I decided to use the reset button itself to allow me to select which kernel and mode the computer is going to run in. So down in this section, we have the stock clock generator circuit. This is the TED chip, which is the brains of the Commodore 264 style of machines, generates the audio, video, and all the clock signals. It's very programmable, and with the clock signal that's sent into it, the kernel is what determines if this is going to be an NTSC or PAL machine. So unlike on the Commodore 64, where you need to have a different VIC chip depending on PAL or NTSC, this one chip is completely programmable for what type of output you want. Since this is an NTSC machine, this clock generator here has a 14.31 MHz crystal. This little yellow variable capacitor here is the trimmer that allows you just to home in on exactly the right frequency. 14.318 MHz for NTSC and around 17.735 MHz for PAL. So if I did swap out this crystal oscillator, I could make this machine a permanent PAL machine, but I really wanted to be able to switch between the two modes. Now this is a very simple crystal here, and you do need to have support circuitry to actually generate a 5-volt clock signal like the type the TED needs. And unfortunately, I need to bypass this entire circuitry. So to do that, I had to actually cut a couple traces on the bottom of the machine. So the clock synthesizer or clock generator is really easy to find online. I bought this one from AliExpress for $2.80. Did have 79 cents shipping, so it was a little over $3. It actually has the capability of generating 3 different clock signals, but for me I'm just using clock 0. Now I have a little highlighter note here. It can generate between 8 kilohertz and 160 megahertz. So the two NTSC and PAL frequencies we need fall well within the range of this device. What's really cool about this device is it actually supports between 3.3 and 5 volts. So that means it's perfect for this machine, which of course runs at 5 volts. And for programming, it just uses a serial line. So there's a serial clock and a serial data line, which will connect to the Arduino for programming. You actually have to use some formulas to program the device to get the exact desired frequency. And I've done that math right here. I'm going to post the Arduino code in the description, and that does all the programming on the fly, but these are the actual two commands that program the device for depending on which clock frequency you want. And what this little board generates is actually a lot more accurate than what the Commodore 16 does with the stock oscillator. So I printed out some of the Commodore C16 schematics. It'll actually be very similar on the Plus 4. But this large chip is the TED chip, and it has the clock input on pin 14. So I've highlighted that in green. And the yellow clock in is coming from that circuitry on the board that's generating the clock. This is the actual analog circuitry that generates the clock. So the yellow clock in is what's going to pin 14 on the TED. And over here on the left is actually the NTSC or the PAL crystal oscillator. All of this circuitry here is to support running this crystal and actually generating a 5-volt clock signal that goes to the TED. But like I had mentioned before, we just need to bypass this entire thing. Ideally, I wanted to make this as easily reversible as possible. So what I decided to do is this TP is a test point. So I took the test point and I soldered a pin header into it. I used this via right here. So this pin header is what feeds the clock signal into the TED. So looking at the board and exactly what I cut, I made a mistake and I didn't put the pin header in TP. I put it in this via right there. And I need to cut right here between R7, so that's +5, that's pulling it up, cut there, and cut on this side, which is the output of Q2. If I cut those two signals, completely isolates this entire section. And if we take a look here, this is R7, that resistor, and this is Q2, that transistor that's generating the clock signal. And on the back of the board, I made a cut right there and right there. This is Q2 right here, so that's the output of the transistor, and this is that R7, that resistor. Now this is completely floating. One other thing to consider is you want to make sure you have a really good ground for the clock signal going into this. It's relatively high frequency, so I decided to put a ground pin right there in the main ground plane. That was sort of the closest one I could find. And I actually power the little clock synthesizer board off of the EEPROM socket, but I take its ground right from here, and then I feed the clock signal into there. And on the oscilloscope, when I look at pin 14, it's a nice, clean TTL clock signal. So taking a look at this EEPROM, there's not much to it. This motherboard can actually accept this EEPROM directly into the motherboard socket without any rewiring. So all I'm really doing with this socket is breaking the connection to A14 so I can control it with the Arduino. And of course I'm pulling power off of the motherboard as well so I can power those circuits. I forgot to mention that of course the power LED has been replaced on this with a newer, higher efficiency one, and I am driving that directly off the Arduino. Here it is, there's a 460 ohm resistor inside in line here, and then I just have some pin headers here that can connect to the Arduino. And let's take a look at the Arduino. So this is just a normal Pro Mini, Micro, whatever clone one. It's a couple $dollars from AliExpress. This is from the code itself, which you'll be able to look at, and I just list out here the various pins that are connected. So the power LED connects to pin 4 on this board. LED alt is basically the onboard LED, so it will flash just so if you don't have the case one hooked up, you'll see it flashing. Address line 14 is pin 5. The reset line, which is sort of an input, except when the thing drives it to load or reset the computer itself, that is pin 6. And we have the 2 pins that go to the clock generator, A5 and A6. It's the SDA and the SCL lines. So on the Atmel MCU, this does vary depending on which MCU is on your board. So you will need to look up, depending on which one it is, which are the SCL and SDA lines. They do move around. But on this particular one, it's A5 and A4. And of course you're going to need a few interconnect lines. So some of these little Dupont jumper cables are perfect. It's very handy to print out a little piece of paper like this just to help you do all the connections. Double check, because you don't want to accidentally reverse polarity, plug the ground into the 5 volts. You could short out the computer doing that. So it's good to have a little handy printout. Let's put the EEPROM into the socket. All right, so on the cheat sheet, reset line is pin 6. So that's this one. A14 is pin 5, so A14 is this orange wire. VCC for me is the white wire coming off the EEPROM socket, so I'm going to plug it onto VCC. and ground will go onto ground. So on this little board, we need to hook up VIN, ground, and the 2 serial control lines. Now remember I said I take the ground for this off of the motherboard right near the TED chip. That ensures a good clock signal. But the VIN, which is the voltage, I do take off the Arduino. So I have an extra pin soldered on the Arduino that allows me to feed the voltage, because there's a voltage pin here and there's another one over there. So I have these wires to go to the Arduino, and it's a little hard to see. So SCL, SDA, ground is the one I don't have connected, and then VIN is the purple wire. So the purple wire is going to connect right there, which is the VCC output of the Arduino. Let's use this black wire here to plug into the ground on the motherboard. So that's going to go right there. And we're going to use this brown wire as the clock output, so output 0. So this brown wire for clock 0 goes onto that pin header on the motherboard, so that's feeding the TED directly. Okay, so SCL is this green or sort of turquoise wire. SCL is A5. So turquoise wire goes to A5, which I think I have to look at the bottom of the board. That's A5. This one next to it is going to be the SDA line. Okay, so at that point, other than the power LED, everything is connected. Let me just quickly double check all the connections. Alright, so I see this is ground, this is reset, where I have this purple wire, which is wrong, because this is VCC to the little clock synthesizer. That's the VCC. This particular Arduino, it's a little hard to see once you solder the pin headers on. It kind of covers up the labels. So there we go. So I'm going to stick these down, but I'm going to just test this out first, make sure everything is working. Okay, here we go. I'm ready. So I turned this on and it didn't work. Do you guys see why? I have the EEPROM over by one set of pins. It's the danger of putting things together while you're looking through the camera. Hopefully I didn't destroy anything by doing this. The plus 5 volts was hanging off the end here, so it actually didn't go into any of this electronics. Worst case, I might have damaged the EEPROM. Let's see. Yeah, okay, so, you know, make sure what you're doing is right. Okay, so this is back in. Double check. It is definitely connected correctly now. I've reconnected everything based on how it should be connected. All right, let's try this again. Hopefully this didn't kill the computer. Yes, all right, we're working. Excellent. And if I push reset quickly, it resets the machine. And if I push and hold, should switch to PAL. All right, yes, okay, good. So we're fully operational. So remember I mentioned a second ago that until the clock generator is programmed, it will not generate a clock which the computer needs to run. And one of the issues is the normal bootloader that's on an Arduino takes quite a while for the Arduino to actually start up. So a microcontroller like the Arduino couldn't start instantly, or nearly instantly. But the regular bootloader is kind of checking for reset signals or whatever. I don't know what it's doing, but it takes about a second or two before it does anything. At the minimum, when the Arduino boots up, it will take a second or two to program this. And that's unfortunate. The computer will just sit there and not do anything. So what I did is I've actually reloaded the bootloader onto here, and I use Optiboot. I can't get into how to program one of these in this video. It's way too complicated, but if you look online, you can see how you load Optiboot onto your microcontroller, onto the Arduino. And with Optiboot, it essentially starts the microcontroller when it gets powered up within a fraction of a second. So the first thing this thing does is it turns on and then immediately programs the clock to generate the frequency to run the machine, and it also pulls the address line high or low depending on what it needs to do. And that all happens nearly instantly. And that's because of Optiboot. So I really recommend that if you're going to do this project, that you also install Optiboot on your Arduino so that you do not have that lag time when you turn the machine on. The power LED is controlled by the Arduino, and it is turned on by the software code that's running on it. So you can tell how fast Optiboot is when I hit the power switch. Listen for the click of the switch to when the light comes on, because that's the delay of when the Arduino is powered up to when it's commanding that this LED turn on. Listen. It's almost instantaneous. With the original bootloader, there's quite a delay there. So it's time to try to mount these inside the case, so it's a little less of a mess and not so dangerous with this stuff floating around in the case. Now I'm going to use this 3M double-sided foam tape, and luckily the motherboard is so small inside the bread bin, there's lots of room over on the sides. So I think I'm just going to stick these down and then use some zip ties to neaten up these wires. So with the clock generator, I want to keep that as close to the TED as possible. That's why I use these little short wires. First, I'm just going to stick these on the back here. I think I'm going to do something like this right here. So I think I'm going to stick the Arduino over here. The reason why I'm not putting it over here on this side of the case is the power LED, which is over on this area, has to reach over there, and that's just extra long. Alright, so let's hook up the power. Keyboard connectors right here, so I want to try to keep these wires away. So there we are, one C16 that is able to switch between PAL and NTSC. Well, that's it for this video. I think that this mod brings this computer up into the 21st century with that modern clock frequency generator to generate the master clock. Having a machine that can run PAL gives you the ability to run the majority of the good software for these computers. This machine was popular in Europe, so most of the good games require PAL to work. And this will allow me to use the best of both worlds. PAL for those games, but NTSC mode if I want to run stuff that does work in NTSC on my NTSC monitors. Anyhow, I'll put all the links to all the parts and all the source code in the description below, so check that out if you want to build one for yourself. If you like this video, I'd appreciate a thumbs up. Please put your comments in the comment section below. If you hate this video, you know what to do. Thumbs down. Hit the subscribe button for more videos, and thanks for watching. Bye.